Welcome to the Wonders of Why channel, where we embark on a journey through the captivating world of science and the perplexing domain of quantum physics. Today, we are about to dive deep into the intriguing concept of macroscopic quantum entanglement. Join us as we demystify the enigma and unveil the profound implications of this mind-boggling phenomenon. To fathom the marvel of macroscopic quantum entanglement, it is essential to grasp the fundamental principles of quantum mechanics. In the quantum realm, particles defy our conventional expectations, as they can exist in multiple states simultaneously, a phenomenon known as superposition. In addition to superposition, quantum particles, such as electrons, possess the ability to become entangled. This entanglement means that the properties of these particles become interlinked, even when they are separated by vast distances. This concept serves as the foundation for the astonishing world of macroscopic quantum entanglement. So, what precisely is macroscopic quantum entanglement? In contrast to traditional quantum entanglement, which usually involves minuscule particles, this phenomenon occurs on a grander scale, involving larger entities like crystals or even entire systems. Imagine two crystals entangled in such a manner that their quantum states are inextricably connected. Whenever one crystal undergoes a change in its properties, the other crystal instantaneously mirrors this alteration, defying the constraints of distance between them. This behavior perplexes scientists and challenges the established principles of classical physics. Temperature plays a pivotal role in the realm of macroscopic quantum entanglement. These entangled macroscopic systems exist in an environment of incredibly low temperatures, nearing absolute zero. Under such frigid conditions, particles shed their thermal energy and settle into their quantum ground states. It is within this icy domain that the delicate web of quantum entanglement between macroscopic objects becomes most conspicuous, allowing scientists to observe and scrutinize this phenomenal occurrence. The potential applications of macroscopic quantum entanglement are nothing short of astounding. One particularly captivating area is quantum computing. The entanglement of macroscopic qubits has the potential to birth quantum computers, with unprecedented processing capabilities ushering in a new era of computational power. Yet another thrilling application lies in the realm of quantum communication. Macroscopic quantum entanglement could pave the way for ultra-secure, long-distance quantum communication networks, sparking a revolution in the field of cryptography. However, amidst all this promise, macroscopic quantum entanglement also presents formidable challenges. Sustaining entanglement at such frigid temperatures poses a Herculean task. Scientists are tirelessly striving to devise novel techniques and materials to surmount these obstacles. The future of this field brims with promise. Researchers are actively exploring methods to scale up and harness macroscopic quantum entanglement for practical applications that hold the potential to reshape our world. To truly appreciate the wonder of macroscopic quantum entanglement, let us delve into some astonishing experiments that have been conducted to showcase this phenomenon. One such experiment involves the cooling of a macroscopic object, such as a minute mechanical oscillator, to temperatures nearing absolute zero. As this oscillator descends to its quantum ground state, it forms an entangled connection with another identical oscillator. The intriguing part is that when one oscillator's properties are observed, changes in the other are instantaneously recorded, regardless of the vast distance that separates them. The peculiar and seemingly paradoxical nature of macroscopic quantum entanglement becomes even more striking when we consider the macroscopic objects involved. This challenges our intuitive understanding, as these objects exhibit quantum behavior on a scale that we can perceive and interact with. Furthermore, this phenomenon extends to more intricate systems, such as arrays of entangled superconducting qubits. In these systems, multiple macroscopic components collaborate, demonstrating quantum effects on a macroscopic scale. However, a significant hurdle in harnessing macroscopic quantum entanglement is the threat of quantum decoherence. This arises when the delicate, entangled state of macroscopic objects is disrupted by their interactions with the surrounding environment. Preserving isolation from external influences becomes a paramount challenge. Scientists are diligently researching methods to shield macroscopic systems from decoherence, often resorting to advanced techniques and materials that minimize any interactions that could compromise the entangled state. The implications of macroscopic quantum entanglement stretch beyond the realms of science and technology. Some theorists even speculate that this phenomenon might offer insights into the very fabric of space-time itself. Could it be that quantum entanglement plays a role in shaping the nature of the universe? While this remains a topic of intense research and spirited debate, one thing is clear: macroscopic quantum entanglement holds the potential to reshape our understanding of fundamental physics and our place in the vast cosmos. As we draw the curtains on our exploration of macroscopic quantum entanglement, we are left with a profound sense of awe. This enigmatic phenomenon serves as a bridge between the quantum and macroscopic worlds, offering a tantalizing glimpse into the extraordinary possibilities that lie ahead in the realms of science and technology. Thank you for joining us on this remarkable journey through the wonders of the quantum universe. One intriguing aspect of macroscopic quantum entanglement is its connection to the famous thought experiment known as Schrödinger's cat. In this hypothetical scenario, a cat is placed in a sealed box with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the Geiger counter detects radiation, the vial is broken, releasing the poison, and the cat is assumed to be both alive and dead simultaneously due to the entanglement of quantum states. While this may seem paradoxical, it serves as a vivid illustration of the bizarre nature of quantum entanglement when scaled up to macroscopic levels. As we delve deeper into the world of macroscopic quantum entanglement, it becomes apparent that this phenomenon is not confined to the realm of theoretical physics. It has been experimentally observed in various settings, pushing the boundaries of our understanding of quantum mechanics. One such experiment involves the use of ultra-cold atomic gases. Scientists have managed to entangle large ensembles of atoms in a Bose-Einstein condensate, a state of matter where atoms behave as a single quantum entity. By manipulating these entangled atomic clouds, researchers have gained insights into macroscopic quantum phenomena that were once considered purely theoretical. Another remarkable experiment focuses on the entanglement of superconducting circuits. These circuits, composed of tiny electrical components, exhibit quantum behavior when cooled to extremely low temperatures. Researchers have successfully entangled multiple superconducting qubits, paving the way for the development of quantum processors with the potential to revolutionize computing as we know it. The concept of spooky action at a distance, as Einstein famously referred to it, remains a central theme in the study of macroscopic quantum entanglement. Even though the entangled objects can be separated by vast distances, changes to one object instantaneously affect the other, defying our classical understanding of cause and effect. Intriguingly, this phenomenon has led to discussions about the nature of reality itself. Some physicists suggest that macroscopic quantum entanglement challenges our perception of a classical deterministic universe and raises questions about the role of consciousness in quantum measurements. The experiments and observations related to macroscopic quantum entanglement continue to push the boundaries of our knowledge. They challenge us to reconsider our understanding of the macroscopic world and its connection to the mysterious and counterintuitive rules of quantum mechanics. Our exploration of macroscopic quantum entanglement has taken us on a journey through the realms of quantum mechanics, from the bizarre behavior of particles in superposition to the entanglement of macroscopic objects on an unprecedented scale. We've witnessed how this phenomenon challenges our understanding of the classical world and opens doors to revolutionary technologies. But as we conclude our journey, it's essential to reflect on the enduring mysteries that macroscopic quantum entanglement leaves in its wake. This enigma reminds us that the universe is far more profound and interconnected than we can fathom. It beckons us to continue our quest for knowledge, pushing the boundaries of science and our own understanding. As we look toward the future, the potential applications of macroscopic quantum entanglement remain tantalizing. Quantum computing, quantum communication, and even the tantalizing possibility of unlocking secrets about the fabric of the universe itself beckon to us. However, these possibilities come with challenges that require creative solutions and unwavering dedication from the scientific community. In closing, Wonders of Why has journeyed with you through the captivating world of macroscopic quantum entanglement. We've explored the bizarre, the mysterious, and the awe-inspiring. We leave you with a sense of wonder and curiosity as we continue to unravel the mysteries of the universe, one entangled particle at a time. Thank you for joining us on this remarkable expedition. As we venture forward into the unknown, may the wonders of science and discovery continue to ignite our imaginations and expand the boundaries of human knowledge.